Namaste and a very good evening to all of you. I welcome you to my channel, The Outlier. My name is Mithun. In today's video, I'll be talking about how to build a deep learning model using Python. Even before I proceed to demonstrate how to build a deep learning model using Python, may I request you to subscribe to my channel, also like and share my videos. Let me begin by introducing you to the data set that I'll be working on. The data set that I'll be working on is the very popular Iris dataset. As you can see here in this dataset, I've got 6 different columns. The first column would be flower ID. The second column would be the sepal length of the flower. Then we have sepal width, which is measured in centimeter. Further, we have petal length and petal width as well. These 4 are variables which are scale variables. They're all measured in centimeter. Let me now draw your attention to the last variable. This is the species of flower. Here we are talking about 3 different species of flowers, namely setosa. We also have other species like versicolor and virginica. The goal behind this analysis would be to predict the species of flower using a deep learning model based on the input features like sepal length, sepal width, petal length, and petal width. Let's now examine the sample size in this particular data set. Let me go to the last row. When we look into the last row, you can see here there are 150 records of the iris data set. So which is a healthy data set for us to kickstart the process of modeling. Let me now apply a filter. When it comes to the last variable, you can clearly see here there are 3 species, namely setosa, versicolor, and virginica. Since there are 3 classes, this becomes a problem of multi-class prediction. There are 3 different classes of flowers that we are interested in predicting, and therefore it is a multi-class problem. This falls under a typical class of problems which are called as supervised machine learning technique. We have a dependent variable with multiple classes, and we have a set of input variables. Let me now go ahead and remove the filter condition. With this introduction about the data set, I will now proceed to Jupyter Notebook. In Jupyter Notebook, we will be seeing how to build a deep learning model. As you can see here, this is an exercise wherein we will be looking at how to build a deep learning model using TensorFlow and Keras. In the first code, what am I doing? We are trying to import the necessary libraries. I repeat, in the first snippet of code, what we are trying to do is we are trying to import the necessary libraries. Let me explain this line by line. In the first line, I'm saying import TensorFlow as TF. What does this mean? This line would help us import the TensorFlow library, which is an open source machine learning framework developed by Google. What are we doing in the second line of code? As you can see here, in the second line of code, we are writing from TensorFlow.Keras.models import sequential. From TensorFlow.Keras.models import sequential. What does this do? This imports the sequential class from the Keras models module of TensorFlow. I repeat, this imports the sequential class from the Keras models module of TensorFlow. The sequential class allows us to create a linear stack of layers for our neural network. Let's now look at the third line of code. Here, we're saying from TensorFlow.Keras.layers import dense. What does this do? This imports the dense class from TensorFlow. I repeat, this simply imports the dense class from the TensorFlow.Keras.layers. In the next line, what we are saying is from sklearn.datasets import load underscore iris. This imports the load underscore iris function from the scikit-learn library, which is a machine learning library for Python. The load underscore iris function is used to load the well-known iris dataset, which contains information about different species of iris flowers. In the next line, what we have is import train underscore test underscore split. Now, this is very important simply because, as the name itself suggests, what we are doing in this line of code is trying to import the train underscore test underscore split function, which helps us split the base data into training and testing dataset. A typical AI model is built on the training dataset. We obtain the results, and once the model gets trained, we will be applying the model on the fresh dataset or the test dataset. The performance of the model is always evaluated on the test dataset. How are we splitting the dataset? You can see here train underscore test underscore split is used to split the dataset. Last but not the least, here we are importing the one hot encoder from sklearn.preprocessing. What does this do? This imports the one hot encoder class from the scikit-learn library. The one hot encoder class is used to convert categorical variables into numeric data. I repeat, this allows us to convert categorical variables into numeric data that can be used for machine learning models. Machine learning models expects that the dependent variable be numeric. In this case, it will be used to one hot encode the target variable in the iris dataset. Once we are through with the first line of code, let's now make a move on to the second line of code. What are we doing here? In the second line of code, what we are doing is to load the iris dataset. We can use a simple function load underscore iris. I've saved it as an object iris. Let's take a peek into the dataset. You can see here, this is how the data is stored at the backend. This displays the records as an array. You can see here, the object is an array. It is made up of lists here. Let me remove this. Let's now move on to the next step. Once you load the iris dataset, the next step would be to split the dataset into training and test. This is where we will be using the train underscore test underscore split. One of the input parameters would be iris.data. We'll have to specify the target here, which is iris.target. As you can see here, we are using 20% for testing the dataset. The remaining 80% is used for training the model. The random state here is 42. When you run the train underscore test underscore split, you will be obtaining 4 important objects. One is the training dataset, which has all the independent variables. Then you have the testing dataset, which has the input variables. Similarly, you'll have the y underscore train and the y underscore test, which is the dependent variable that we are going to use for training and testing respectively. Let me now scroll down. You can see here one hot encode the target variable. What are we doing here? When we talk about one hot encoding, there are a few things which are happening in this line of code. Let's examine what we are stating in this line. It says encode.fit underscore transform of y underscore train dot reshape of -1, 1 to array of. Let me draw your attention to y underscore train dot reshape of. I'd like to take this opportunity to explain this in detail. Y underscore train dot reshape of -1, 1 is used to reshape the target variable y underscore train. As the name itself suggests, this is used to reshape the target variable y underscore train into a two-dimensional array with one column and an unknown number of rows. The -1 that you see here in the reshape function is a placeholder. I repeat, the -1 that you see here in the reshape function is a placeholder. What do we mean by a placeholder? When we say the -1 in the reshape function is a placeholder, this means that the number of rows is unknown and should be inferred from the number of elements in y underscore train. Once we have reshaped, we will be applying the fit underscore transform. What is this fit underscore transform? Fit underscore transform is a method of the one-hot encoder class. This performs both the fitting and transformation steps on the data. I repeat, the fit underscore transform does two tasks. One is it fits as well as it transforms. Both these activities are performed at this level. It learns the encoding scheme from the training set and applies it to the data. In this case, it is applied to the reshaped target variable y underscore train. Now, let's look at dot to array of. As the name itself suggests, to array of is a method that converts the output of the fit underscore transform method to a dense NumPy array. This is necessary because the output of the fit underscore transform is a sparse matrix, which is a matrix where most of the elements are 0. The resulting y underscore train is a dense NumPy array with the same number of rows as the input y underscore train, but with one column for each possible category in the target variable. Each row will have a value of 1 in the column corresponding to the category of the flower and in all other columns. This one-hot encoded format is commonly used in machine learning algorithms to represent categorical data. So this is what we are doing at this stage when we say to array of. There are three things which we are doing. One is reshaping, that is followed by fit underscore transform. And at the last level, what we are using is converting this into an array. Let's now go to the defining the model architecture part. What are we doing here? There are 4 important statements here. The first statement here is model equals sequential. Note that this is almost like specifying the architecture or the blueprint of the neural network model. When we specify model equals sequential of, this line creates an instance of the sequential class, which allows us to create a linear stack of layers for our neural network. This is the first line. Sorry, this is the first layer. What is happening in the first layer? As you can see here, we are using a dense class. In the first layer, when we use a dense class, what it means is that the dense class is used to create a fully connected layer with 10 neurons. You can see here, when we specify 10 here, it means that there are 10 neurons. Further, when you look at the input shape, we are specifying the value of 4. The input shape parameter specifies the shape of the input data, which is a one-dimensional array with 4 features in this case. Remember, the input data has petal length, petal width, sepal length, and sepal width. The activation function that we are using in the first layer is the ReLU activation function. So this is as far as the first layer is concerned. Let's now try to understand what's happening in the second layer. As before, we are using a dense class, which means that this is a fully connected layer with 8 neurons. The activation function here is a ReLU activation function. In the final layer, what we are doing is we are again using a dense class. Here we have a fully connected layer. I repeat, here we have a fully connected layer with 3 neurons. Why 3? Because 3 corresponds to the 3 possible categories of the iris dataset. We are using the softmax activation function. Now, the softmax activation function is used to convert the output of the last layer into a probability distribution over the 3 possible categories, which can be interpreted as the predicted probability of each category for a given input. So this is what we have under the model architecture. Let me go ahead and quickly execute this. In the next stage, what we are doing is we are trying to compile the model by specifying a loss function. The loss function that we are using is categorical underscore cross entropy. So this is the name of the loss function. The optimizer would be Adam optimizer, and the metrics here would be accuracy. There are different metrics that you could use. However, for the purpose of this video, I'll be using the accuracy metric. Let me go ahead and compile the model. So you have defined the model architecture and then you're compiling the model. Let me scroll down. Here we are doing what is called as training the model. How do you train the model? All that you need to do is run the model.fit. The input parameters here would be the independent variables from the training dataset. We have to specify the dependent variable for the training dataset. The epochs would be 50. You can experiment with a different value as far as epochs are concerned. The batch size is 10 and the validation data will be x underscore test and y underscore test. Let's go ahead and execute this particular model. You can see here what is happening in epoch 1. Epoch 1, you can see here the validation accuracy is 36%. In the second stage, again, the validation accuracy is the same value, 36%. In the third epoch, the validation accuracy has jumped to 43%. Further, it has reduced to 40%. Let's keep a track of this. 36%, 36%, 36% in the 7th epoch, and in the 8th epoch, the validation accuracy is 40%. Let me scroll down. You can see here there is a massive jump in epoch number 10. In epoch number 10, we see the validation accuracy to the extent of 76%. In the earlier iteration, the epoch was 53%. So there is almost a 23% jump in the validation accuracy. We want the validation accuracy to be close to 1, because closer the validation accuracy to 1, it means that better the training of the model. Let me scroll down. We are right now seeing the 43rd epoch, and here we have the 50th epoch. So this is the last epoch. You can experiment by giving 60 epochs or 100 epochs as well. And you can see here the validation accuracy in this case is 96.6%, which is not bad at all. It's a high number. Let's finally evaluate the quality of the model that we have built. This is the test accuracy. The test accuracy is the number that we get in the final epoch, which is 96.6%. The accuracy is a value which lies between 0 and 1. If the value of the accuracy is closer to 1, it means that the model is a good model. If the accuracy of the model is less than 50%, it is usually not an acceptable model, and we need to do some hyperparameter tuning to improve the performance of the model. What I'm now going to do is quickly run through some of the important steps. You can see here, in this particular deep learning model, we are importing the necessary libraries in the first code. Then we are loading the iris dataset. Further, we are trying to split the dataset into training and test dataset. We will be using the one-hot encode on the target variable. Next, let's define the model architecture, and we can go ahead and compile the model. In the next stage, what we are doing is we are training the model by using 50 epochs. We are specifying the batch size here as 10. When we look through the accuracy that we are obtaining in the validation sample is 96.67. As a final step, what we have done is to evaluate the overall performance of the model, which comes out to be 96.6%. With this, I have come to the end of today's video. In today's video, we've seen how to build a deep learning model using TensorFlow and Keras for the iris dataset. I thank you very much for watching this particular video. I request you to subscribe to my channel and like and share my videos. Thank you very much once again. Have a great day ahead.